Thank you very much. So the talk will be about failure. No, about the successes we can learn from failure. I have a much more modest experience than Professor Makowski, who said things which I agree with. But in the last 12 years, I have taught around 1,000 computer science students, trying to teach them logic and trying to learn from their failures and from my failure in teaching them. So just as a word of warning, I've also taught a lot of philosophy students, less than computer science students. And then I try to find ways in which they can agree and which they can learn with each other. So the words I have just put there are episteme and techne, which are important words I would like to remember, connected to knowledge and connected to what we have just seen, that knowledge of theoretical orientation and practical orientation. But this talk will be more about my opinion, doxa, and heuristics related to teaching. And I would like to stress, and I'll have some examples on this, philosophy has been using this for a long time, analogies in trying to teach things, in trying to orient the minds of people to learn things. And I think computer science has a lot to offer in terms of analogies, if only you know a little bit. As a way of an example, I could mention, for instance, the analogy in between the software and hardware and the mind and the brain, which is you don't need to know so much to understand. The philosopher can understand, even though even if she has not studied programming. But if I would like to make another analogy, for instance, in between the role of discharge of assumptions in natural deduction and the destruction of local variables in programming. This would be an analogy that the computer scientist would say, now I understand what you mean by these local variables, by this discharge of assumptions. And the philosopher might look and say, well, you didn't illuminate me so much. So the analogies depend a lot on what's the audience in which you direct them. And most of the things I will be discussing demand that previous study in a little bit of study in computer science. Okay, first I would like to make a poll with you, if you allow me, because that's for myself. I'm very interested in knowing what you will say about these kind of things. Imagine you have this button, blast, that helps you improving things. And let me put this in a bit more specific way. There is you, a mathematician. You might think of it as you. And there is Charlie, who is the assistant, very competent one, and that he could call to help when he needs to prove something. Okay, I would like to know your opinion. Really, I would like you to raise your hands. So if you could call Charlie to help you, but you could only call him once because maybe he's very busy or you don't have time yourself to do this every now and then, would you, when approached to a conjecture, would you try first to go as far as you can and then call Charlie to help you? Or would you press the button, call Charlie right at the beginning, and then try to intercede and help if he didn't succeed in finishing the proof? So that's the situation. Maybe there is more time for interaction later on. Maybe you can do another round after this, but imagine you have just one round. Which of you would first do it yourself and then call Charlie? Oh, I guess it's most people. Who would call Charlie and then do it yourself? Okay, you don't trust Charlie that much. Good, thanks. Thanks very much. I will just ask you two more things, but you don't need to vote on this. But would you consider changing the vote if you now learn that Charlie is a computer? Maybe you would, or maybe you would not, because he's not spending so much of his time, right? If you just press the button, he's a computer, he doesn't care. What if it's not you, but it's one of your undergraduate students? Would you allow him to start, or would you push the button first? Okay. Now, proof assistants have been used for a while. You won't see any in this talk, but I'll talk about them. They have been used for a while to prove things, or to help people prove things in the computer. I mean, the proofs are done in the computer. That means that It could mean a lot of different things. So, for instance, it could mean that you're using the computer for an exhaustive checking of a lot of options, that you're generating models or generating proofs, that you're just verifying the proofs, or that you're using it to implement some decidability procedure. I won't be talking about these very much advanced use of computer in proofs, because I want to talk about the use of computers in teaching. Okay, so I will put some lessons. I call them lessons, but you might read them as outrageous suggestions. So the first one is that if we really want to teach for pedagogical purposes, perhaps it's better not to automate too much, or at least to try to control as much as we allow automation to crop in. And that might be for various reasons. It might be just because you think that people are pushing the button too much, and they're not really trying to understand what's going on before doing that. Okay, for a contrast, I come from an underdeveloped country in which if we had these very elaborated dolls like you had that could play by themselves, you just push a button and they would just go in and doing things brought from the United States or brought from Europe, we would be very, very excited. But we were excited for 5 minutes or so. And then the doll was playing by itself, and then it would be just so much better to go and do something that was more open to our imagination. And the wooden toys were usually much more interesting in that respect. Now, of course, using an assistant might be also interesting. And a combination of this with the wooden toys might be the right way to go. But, and that's not, there's no button pushing there. The assistant might decide not to work, or the assistant might think that she's not having so much fun, or that on the she's taking control of the situation, so it's so nice. So it might, there's a lot of interchange going on in this respect. Now, this has already been raised, and it will be raised again during this, this conference, about what are the skills we should be teaching. And I will contrast them with what we do in computer science. I don't know about your students, but my students in Brazil are not necessarily have the right upbringing. They do not necessarily arrive to the university knowing as much as I would like them to. So does anyone of you know what this is? Okay, maybe you have been in Rome, because I had to go there to see it. It's not very common elsewhere. It's a Romanesque broccoli. It's not a fractal, and it's not a broccoli you find everywhere, but it's a Romanesco broccoli. Most of my students wouldn't know the difference between this and a proof. So that's the analogy that I wanted to make. Well, but now you imagine, if people come to you and ask you, is this correct? Is this proof correct? If they need to ask that question, which a computer wouldn't ask, that already means that they do not get the whole point of what a proof is, right? But it makes sense they should ask, because they're learning to recognize it. And they might have trouble recognizing. And I think that the way of helping them with this problem is focusing on know why instead of know how. So I usually equate know-how with something that you learn when you're doing a technical course, which is not to put it down. It's very important to do this technological upbringing, to have people that really know how to do things. But if you want to teach things to people that they will learn a few years later, and that they will still remember a few years later, and that it probably wouldn't be linear algebra or determinants. You could learn them to prove. You can learn them to redo a result that they have learned before. You can try to teach them tools so that they're able to recover things that they have learned before. And to learn that, they need to understand the why. And that's one thing that we discover after a while, that it's better not to stress too much in content, but on the form or on the tools that make the content available to them. Okay, just a little bit more on this. This relates to my topic on formalized math. I like very much this recent quotation by Gontier, who works for Microsoft here in France, saying that if we're talking about a proof written in the form of a program and a formal proof, It should not only have this recipe that describes what the machine should do, but it should also tell why the machine does it. So it's related to what I was saying before. And what is why in this sense? Why in this sense would be a way of verifying that this has been done correctly. I will not enter in detail into this, but this is what would make a blind, stupid, button-pushing proof different from one in which you know what you're doing. Of course, it's difficult to guarantee that you know what you're doing, but that's what we try to do. Let me just make an analogy, an analogy that I have found it very instructing for computer scientists, and which mathematicians find it hard to see, which is about the variables, the meaning of variables. You know, we're in this enterprise since God told Adam to do it, to name things in the world. And there are a lot of things in the world that would like to name. Perhaps would like to name sets and types, morphisms, predicates, and functions, constants, variables. Well, variables? There is nothing like a variable entity in mathematics. So why should we name it? It's better to give names to things which don't exist. What would be a variable entity? It's an entity that you look at it, and then you look again, it's a different thing. It's a quantum thing. It just fluctuates when you look at it again. There is nothing like a variable in mathematics or in natural language, but there are things that you use to refer to them. Let me just give this example on variables, and I would like to discuss very briefly the role of variables through the binders. So this is not original. It's just something I found in other places, but I like to point it out. So instead of asking about the role of the variables, I'm asking about which variables do these expressions depend on, the value of this expression depend on. So it's a summation, and if you look at it, of course, there is some role, there's some place for you choosing what to do, but you might want to say that k is a constant or a variable, free variable. You might want to say that m and n are constants or variables, but you need to say there that I is a bound variable. And being a bound variable has a lot of interesting effects. In particular, you could change the name of it. It doesn't matter what's the name that you give to it. It's a placeholder. So that far, a mathematician will see. He'll just not call it a bound variable, that he understands what it's about. What does a computer scientist does about it? If he's programming in imperative language, he's using this to do a loop. Or he's doing this recursively, he's using this to just as the name of the variable over which he's doing the recursion. Now, for another example, we have summation, now we have products. What is that? That's a specific number, right? It's just a specific number. What's the role of k there? K is just a bound variable. Why not writing like this? Okay, so all bound variables could be eliminated by the change of formalism. And sometimes people don't stop to think about it. When you show this to computer science students, they say, now I see what this math is about. It's about programming. Okay, so the dummy variable disappeared. The same about unions or intersections of arbitrary families. I will not even try to answer. This is clear what it should be. Again, in mathematics, you see a notation like this. So what are the variables there? You have k and n. Well, n obviously is bound, right? And actually, this is just a way of talking about 0. Okay, and what is that? That's definition of derivative. If it exists, it's a specific thing. So in that place, you have h as a dummy variable. And a is free, or a constant. But what about f? That takes us to second order logic, right? This is a functional symbol. You could be quantifying over it if you want. And this could be a variable, but a functional variable. But okay. And what about this? This has a specific variable. Can you calculate this? Okay, it's not difficult, but it has a specific value. And again, we all learned in calculus that we shouldn't mess with the x in dx. And that's for a specific reason. It doesn't exist. It's just this bound variable. Okay, so the lesson for the students in that case is that they should know their variables. Okay, and how does that relate to formalized math? Well, in two respects. There is formalized math in which students are involved in implementing, and there is one in which they're involved in using. Implementing this is already quite interesting because they have to learn how to put these bound variables there somehow in a way that they don't really, that their names are not really important. There are ways of showing this, for instance, using De Bruijn indices, or there are ways of using this together with alpha conversion to be able to say that it doesn't really, you don't really care about the names of the variables. But it's a challenge to be able to understand because it's a very different role that bound variables have than free variables. And for the users also, they will have different rules connected to these variables, rules that relate to parameters and rules that relate to unknowns. And they might even have schematic variables in their languages. Okay, there are two more things I wanted to say about this. I think the whole idea, the whole definition of proof theory is wrong. I shouldn't. Is there any proof theorists around? Okay. I taught a course with the proof theorists in the last semester, and I think there are a lot of important things missing. I have to say that I come from this profane tradition, not the sacred tradition, so I find it not hard to ask about this. But imagine you want to prove a result like that, a simple result in set theory. You could just write the proof. Okay, I was imagining I could do the dynamics here because I want to talk about dynamics. So I was imagining I would be able to write this proof in a certain structure in front of you. But you can imagine, as you see, you have 1, and then you assume 2, and then 2 takes you to 3 and 4. Then from 4 you go to 5. Then 3 and 5 gives you 6, and so on. So there is a structure behind this, and it's not only that. If I had done this exercise in front of you and now presented to you this specific structure, either in the form of a directed acyclic graph or in the form of a derivation tree, at the end, if I ask you to forget what I just did and looked at the final proof, it's just looking at this text. You don't understand it just by looking at it. You have to go through it. So there is something important missing in the definition of a proof, I would contend, which helps the students a lot, is to think of it as something dynamic, is to think of it as something that is built, and think of it as a movie and not just the final frame of the movie. So I would contend that proof theory should redefine their objects and not as the derivation trees, but the sequence of steps, sequence of derivation trees or collections of derivation trees that take you to the final step. And there was another thing I wanted to propose, which is in the paper. Actually, most of the things I mentioned here have almost zero intersection with the example I use in the paper. And I do the example of the importance of strategy in the paper. So I invite you to read, because I'm not going to talk about it. But I think also the definition of a proof system should come together coupled with a notion of strategy that you should choose, and there are examples in which this is really important. Okay, so on the side of formalized math, you see that the way we have been using it with students is that they have to describe their proofs, and they describe in a specific proof language, and they write these proof scripts that they can execute, and they can see stepwise how it builds this sequence of derivation trees or collections of derivation trees that take you to the final step. And they can understand because they do it themselves. It's like they're writing their own movie and writing the script of the movie and running it. And myself, I can also understand, I can tell you much better if I execute the program than if I just look at the final step. And I can check the program. Okay, so the last thing I wanted to mention is this. It's another thing that I found to be very important in teaching students was that they often learn some definitions, but they don't learn what to do when these definitions do not apply. Let me give you just 3 simple examples of this situation. For instance, imagine I tell them that they have a given in the form, the negation of a conjunction. So the conjunction is false in the classical case. How should they use it? Well, if it's a given, they could use it by saying, well, there are 2 cases. Either the first side, the left-hand side is false, or the right-hand side is false, and the reason from that. If they have to prove it, they have to prove one of these 2 sides. And they didn't learn that directly from the definition of conjunction, But they did, in a sense, because it's an if and only if. Now, let me go just a little bit further. You teach them well, maybe you're able to teach them what's the semantical consequence, what's entailment. It's quite hard. It's hypothetical, and some students never go as far as learning what it means. And then you tell them, okay, but now prove that phi is not a consequence of gamma. And a lot of them have difficulty because they did not really understand the thing as an if and only if, and they cannot do the negation of the concept, and they cannot immediately see that they need to present a counterexample, or present a counter model. And for a final example, this is a provocation for you. Does any of you know what to do if you're given something of this format as a given, and I tell you to use this to prove something? You could use the negation of a conjunction, probably, but can you use the negation of set complement? Maybe you have to think of it, because you haven't learned the rule, but actually this is just an implication. And using it is just like using any implication in modus ponens. I give you A belongs to B, and then you have to prove that A belongs to C. Or you get A belongs to C for free. Okay, so as last 10 seconds of advertise, in this afternoon, there will be a tool being presented incorporating some of the ideas and lessons that I have presented in this talk. Thank you very much.
I like your notion of analogy, but it applies actually in the following sense. A proof is like a score, and understanding the proof is like playing it.
Yes.
But having a computer understand your proof is like playing a CD. And if you don't know how the CD has been produced, it's completely useless. So the proof assistants, I'm not sure they really capture what you play your violin sonata and then you hear the CD to verify that it is similar. But you have to play your violin sonata, not the computer. Just the fact that the CD represents the score without being able to play the score is a meaningless statement.
Yeah.
So the same is true about proof.
I agree. And in this tool, for instance, we practically forbid that the students do any automation. So they have to play it themselves, but they have the computer to assist and check, well, you didn't do a wrong step. Because, you know, the paper media is very bad. It doesn't say anything to you. And the computer just assists. And that's where we have been using it.
I agree very much with what you were saying about proof being this dynamic process. I've seen one of these modern videos aimed at trying to teach new university teachers how to teach, and I saw one which contained a shot of a mathematician standing at a blackboard writing a proof down, and the audience was expected to laugh at this as an example of bad teaching.
All right.
Whereas this can actually, as anybody's
It was probably the best.
this would be absolutely superb because you're matching to the speed of the audience, they're writing down, you're talking and all this. It's exactly proof is dynamics, and it's exactly the thing, as you say, that it maybe contains a thing that's not contained in formalized improved theoretic analyses.
Mm.
So that very old-fashioned form of teaching can be actually superb.
Well, I can tell you that the first time I really remember having seen real math in front of me was when I went to this Institute of Pure and Applied Mathematics in Brazil. And there was an algebra professor who wrote the book, and he was teaching from the book, but he never looked at the book. And he just went there and said, okay, so what should be proved now from what I said before? What is the obvious thing to do now? And then he was just wondering what it would be. He would write a statement which was almost always wrong, try to prove it, and at the end he would say, whoa, that's what I really proved. And he would do this in front of us, never looking at any piece of paper, and this was where it was really happening. And I could remember afterwards the process, because I've seen it happening in front of me.
Yeah, I would like to make a comment on lesson 5. Where indeed you said that well, students or say should be able to know when definition apply and when they do not. And I believe this is a very important point because it happens in the very early stage for students. And I believe mathematics becomes hard to teach also because mathematics has its own way of defining objects which are defined in a non-trivial way. And I think some students simply do not understand the objects that are defined just because they're not even able, to split between implies and or. This is something which has this or this and not that. So yes, I think it's very, very important, and I recently have asked students to negate a mathematical property, which would say that not phi is a tautology or psi is a tautology, and obviously you can imagine what could happen, and yes.
I can imagine. I've been doing this systematically with my logic students for a few years. I'm not saying that I have succeeded very much, but every time I introduce a new concept or a new object, I try to ask them to produce a counterexample to show me something that's not this kind of object, and to tell me that what happens when this property fails, and give them examples of producing these kind of things. I think there are no books in the market doing this systematically, or there are very few books doing this systematically, and this is what I wanted to push.